All right, now we have Darrel Newsom, and he's the city manager from Wolfforth, Texas, and he'll be giving us the information on his project.
Good afternoon. Pleased to be here this afternoon. Great to be here with you guys. This is my first time to attend this conference, and it's a great conference and that type of thing. And I've worked with Jason at High Plains Underground Water District over the years, and Jason asked me to come to talk to you guys a little bit about some of this. And first, let me tell you a little bit of history and a little bit about Wolfforth, Texas. Wolfforth is right on the edge of Lubbock. It's just right outside the loop of Lubbock, and we touch city limit signs. And so that means that we're right on the Ogallala. But the city, the ground is all groundwater. We don't have any surface water. We don't get any water from Lubbock. We don't buy from other cities. It's totally groundwater. So we have 16 producing wells in the Ogallala. And so those are different depths, varying depths, down to 200 feet or so. Saturated thicknesses are about 45 feet. All of that water, we have different levels of production in that water, anywhere from 35 gallons a minute up to 150 gallons a minute. So the wells are not very forthcoming. So it's pretty tight up there. We also are in a high growth area. Lubbock is growing to the southwest, and we since the 2010 census, when I first became city manager, which has been almost exactly 10 years, we've grown over 70%, and any of those growth rates can be anywhere from 6 to 13% per year. So we're being hit pretty hard with a lot of growth, and during that time we haven't expanded we've drilled a couple of new wells, but they're not in production yet. So I'll talk a little bit more about how that's worked out. But we have a certain number of technologies for a small town. We try to be ahead of the game. We've implemented a small GIS system. It's very unsimilar to what most of the larger systems and towns have. But we also, for quite some time, have used SCADA for all of our well control systems and controlling our water towers and that type of thing. But we are fully electronic read meters, ARM completely across the town. So we are fortunate in our size but we've grown. But as we've grown, we've been able to implement technologies a little bit easier than a town the size of Lubbock or the larger cities could do. Our storage, we have tried to expand our storage as we've gone along and move along with those kinds of things. One of the things that I primarily want to talk to you about this afternoon is electrodialysis reversal. This is the technology that we picked to upgrade our water quality. We have a lot of talks at these conferences about volume and where to find more water and that type of thing. But due to regulatory issues, we had to correct some of our contamination issues, and I'll go into that in a lot of detail about the electrodialysis reversal. And then also, I have a little trouble with the slide there. I talked a little bit about the electronic read meters in there. A couple of things we've done that are kind of interesting. Our GIS allows us to work with all of our infrastructure utilities. This is kind of just a skeleton type view of our town, but when we're able to, we have layers in our GIS that allow us to look at our water system in any format and kind of drill down into what our water system is doing at any point in time. We could look at our meters, our fire hydrants, our flows in our fire hydrants, those types of things. So this is by a company out of Marble Falls called 3CGO, and we use their GIS. One of the interesting things that we've done to try to keep up with some of our maintenance and some of our the things that we do to our wells is each well has its own website, and so that's kind of an interesting concept. But we go all the way back to the drilling logs if we had them. Most of our wells were old farm wells, actual irrigation wells from back in the past, and so we've taken all those old drilling reports. We've taken any logs or any type of workover that we've done with them. But one of the main things we do is we've purchased our own camera system, and we do downhole videos every time we pull the pumps and see what kind of progression we've got in the maintenance of the well. And that's been very helpful to us to have that individual. We just use Google, and we use a process called Google Sites. And so that's how we keep up with those things. But there's an example of one of our original well logs from probably back in the 40s or 50s. Here's kind of a snapshot of our SCADA system. This shows kind of the activity and just a dashboard for the system, and you can see all of our elevated towers. We can see how many wells are running at any point in time. And for a town our size, we run with a pretty small public works department because a lot of these functions are automated. This kind of shows an example of our elevated storage and how it progresses during the day and over the evening. But these graphs are helpful to us to see where our peak times are. A lot of times, as city manager here, I get a lot of questions from Texas Tech comes over and wants to do a lot of projects with us. And we've even had high school students that are interested in doing projects, and they want to know how conservation and storage and all these other factors affect our water. And really, this graph is just kind of to show it's really hard to get a handle on that because most of what we produce for the consumer is used, or the highest portion of the usage is for landscape irrigation. In the wintertime, we average maybe 650,000 or a little bit better, of usage. But in the summers, it more than doubles that, and so most of that goes to landscape irrigation now. And you can see the gold bars on the right; those are this year's water consumption. Our growth has continued to come on at a very high pace, but you can see this year we haven't used as much water. It's been a little bit wetter year earlier in the spring, and it's kind of like Senator Perry said this morning. Now we're back in a drought area. So let me go back and I talked a little bit about electrodialysis reversal, and this is what we want to kind of focus on this afternoon. But let me, if you guys can play the video, we might see if we can get that to work. This is a very short video of how the filtration technology that we use works. There you go.
Water, with all its beauty, has an interesting adventure as it flows through the environment. As it moves in swiftly flowing rivers or slowly in lakes and through the soil, water picks up minerals and salts. These salts and minerals are naturally occurring, and they have a variety of uses when they are in solid form. But water, because of its polar molecular structure, can dissolve salt. When this happens, salt is broken up into individual ions. The positively charged ions, like sodium, are called cations, and the negatively charged ions, like chloride, are called anions. When salt is dissolved in water, these ions move freely through the water as individual atoms. Sometimes the concentration of salts and minerals can be too high for drinking water, industrial use, or irrigation purposes. The process of removing salt from water is called desalination. Ions such as salt have the ability to move in water if direct current electricity is applied to the water. The negatively charged chloride ion moves to the positively charged anode under the influence of electricity, and the positively charged sodium ion moves toward the negatively charged cathode. Electrodialysis is an advanced membrane technology that utilizes this ion movement to desalinate water. With electrodialysis, the ions move through special membranes and create two separate streams, a desalinated stream and a concentrated salt stream. In addition to using electricity to move and separate salts from water, electrodialysis also uses electricity to clean the electrodialysis cell. In normal use, salts and fine organic material may tend to accumulate on the membrane surface. But By reversing the flow of the applied direct current, salts and organics are driven back into solution and cleaned off the membrane surface. When many membranes are combined, a full-scale membrane stack is created. And this membrane stack is usually one of many stacks that are used for a large-scale electrodialysis reversal plant. This is how electrodialysis reversal technology is used to transform previously unusable saline water into a new freshwater resource to create water for food, water for industry, and water for life.
Yeah, they've rebranded that particular video. That when we first started dealing with GE was actually the technology or the company that started this or started with this technology. They actually purchased the company and started doing that. So I wanted to kind of give you an overview of EDR before I started talking about how we got to this point. This is a picture of our plants. We have, at this point in time, we have three what they call trains, and those consist of those stacks that she mentioned in the video. And so we're actually in a two-stage process, treatment process, to use these through the stacks themselves. Once again, they all talk to our SCADA system. It's all electronically controlled, very automated process. And this is kind of one of the stacks, or a couple of the stacks without their clothes on. And this is what they look like when they're uncovered. But there are around 1,600 membranes stacked in that individual stack. And so this is what they look like when we actually maintain those. Those are actually can be taken apart membrane by membrane. So how did we get to this point? Well, I can't remember. Probably somebody in here will probably remember better than I can when actually TCEQ changed the requirements for arsenic and fluoride. So in our local water and our groundwater, we have pretty high levels of fluoride. We're around 5 to 6 parts per million, and then in arsenic, we were, depending on the well and where you picked up on there, you'd be at in fluoride we'd be as high as 18 parts per billion, At the point it used to, the MCL used to be 50 parts per billion, and they lowered that standard. So we became non-compliant. The water didn't change any. That's kind of hard to explain to your citizens that the water didn't change. We weren't putting arsenic in the water. There wasn't any, type of process that caused that, but just the standards changed. And so, so the TCEQ came to us and started talking to us about mitigating those two components, and then so we started looking at technology. We started looking at RO and trying to find out what was the best option on that. Well, with our water scarcity in West Texas, RO we felt like was too much loss in the treatment process, and so you could have a pretty high level of loss in the RO. So we established this as being a good technology for us to use. But one of the problems that we found when we made the site visits was that you had to do something with the brine stream. She talked about the concentrate in the video that you saw, and so that became problematic with TCEQ. Nobody wanted to tell us or give us the release to do anything with that brine stream. We talked about potentially putting it in or just putting it on the parks or putting it in a park lake or just running it down that way, and that was unacceptable. We talked about doing some ag type of application that wasn't acceptable. So that really extended the process for a long time because nobody really wanted to deal with the brine stream. So it was also an emerging technology that's been used in some other areas, but in a drinking water format, TCEQ was pretty uncomfortable with it because it was such an emerging technology. Also, as we went along with this process, the EPA got involved. So ultimately, that really stepped up the time frame. TCEQ, at that point in time, was kind of out of the picture. We started dealing with EPA, and we got enforcement letters threatening fines of up to $38,500 per day, and that was for just the arsenic alone. And at a later point in time, we got the same kind of enforcement letter for fluoride. So if we were non-compliant at some point in time, we were up to about $80,000 a day looking at those fines. And so we continue to try to move the process and try to move along. So one of the things that we utilized in the process was we looked at our whole water system because we felt like some things had gotten behind. So not only if we were going to do this extensive storage process, we were going to have to do some other things to our water system. So we started working on the design process with GE, and they use a system called WATSIS that does water analysis, and gave us kind of an end product that we needed to shoot for, and that started helping them with design. So this was quite a long, drawn-out process. So while they were working on that, TCEQ required us to do a 90-day study. And so that study was a containerized system that they shipped out, and that thing was approximately $150,000 study. So as a part of our whole budget, it was a pretty big chunk. And so I've kind of got some dates here, but it shows you how long the process took to get all this done, and how long. So from the original orders until the time we got finished, it was a pretty considerable piece of time. And so it's for a town our size at that time, we were about 1,200 water meters. We're currently 1,900 water meters, so that gives you an indication of the growth. But when you take on a big debt project like this, the financing is pretty simple. You divide it by the 20 years, and you divide it by the number of water meters, and that's how the impact hits that's how it hits your customer. And so at the time that we did this, it was about $28 or $26 per water meter. By the time we finished, it was up to about 28. So it was a fairly high percentage in terms of our customers' water bills. And so, one of the things that we got into with GE, I don't know that it would be that situation with Suez anymore, but we couldn't get the P&IDs to actually finish the design of the plant until we paid for the $1.5 million for the system. So that kind of strapped us and held us up for a little bit there too. So while we're working on the regulatory issues and trying to get all this done with TCEQ, one of the things we knew we needed was additional storage. And so, what we were working on is we had about 750,000 gallons budgeted in storage, and I believe it was preload. Well, Caldwell Tank came to us at that time, and they were having a little bit of difficulty competing in this market. But kind of a long story short, we were able to purchase the 1.5 million gallon storage for about about what we had budgeted for 750,000 gallons. So we were very fortunate in that type of thing. So pardon me, I have to give my gap. So along with this, we finally got along into the spring of 2014 and began construction. It was very difficult to get this going. The electronics of this type of product was the grounding in and of itself was just a massive project. As we went along, we got all this put together. These are some dates that we've got in here that ultimately we moved along to, but it took us about 2 years to get the plant built. But an interesting story, we finally got the plant built, put together, and got it done. And we'd had it running for about 6 weeks, and of course, the consumers had heard all along that we were building the project, and we were we'd raised their bill for a couple of years because we'd already, started paying for the debt. So at the point in time that we had it running, we'd had it running for about 6 weeks, and we were testing. We were actually kind of wasting a lot of water in the testing process. And so finally had a consumer call and asked why were we not turning that on? And I went on to explain that TCEQ had not turned it loose yet, that we were just not ready to, or they weren't ready to do that. She said, well, is there anything I can do? So she actually called TCEQ and complained and told them, look, we've had water issues for a long time. now we've got a perfectly good water system. Why can't you turn it over to us? And, surprisingly enough, that one phone call got us started in this whole process. It was amazing that one phone call got it knocked loose. By the end of that evening, I had a letter that said we could start production in the water at midnight that night. So it was kind of an interesting process. So it's been a great process. We just to give you kind of an idea of we're at a 75-25 blend with the water and raw water and treated water, and that's knocked our total contaminants down to a very acceptable level. Our arsenic is almost immeasurable. Our fluorides are a little above what TCEQ would like us to turn up the inputs on the plant and get our fluorides down to a 2. But we don't really want to eat that cost to be able to get it down to that level. So we've got wanted to show you a couple of things on here. Our acid production. Our acid is in there to change the pHs, but that's the way the system is cleaned. The reverse dialysis reversal process uses some acid in there, and so we've got a couple of things that we need to that are really causing us some issues. We have a lot of sand and a lot of manganese, and we're expecting to have to go ahead and do pre-treatment now, and we hope that doesn't waste any more water than we are. We're very happy with the fact that we are down to depending on the time of year, that we're pushing anywhere from about a 6 to a 10% loss on our treatment. So it's working. That's been very effective and working out really well. And we're testing different types of pretreatment. We also came up short in understanding how much acid we'd use to clean the plant and how much we were working with. So we're working to change that. Our first will be the pretreatment, though, because of the sand and manganese that we're capturing. We want to try to mitigate that issue if we can. So we have some issues that we're still. I think we've got TCEQ pretty happy with us. I think Water Development Board is recommending this technology to some other locations that have got issues with arsenic and fluoride. It's been helpful for us to have taken care of all this for some of these other communities. I think they're still being requested to actually pilot that, but we've got some other options up there that we're looking at in the future, but we're talking about expanding our well farms. The Water District's helping us with doing some testing in deeper Edwards Trinity High Plains. We've looked at the documents, way too brackish, way too salty, I think, to be practical at this point, but Edwards Trinity High Plains may be an option. And so purchasing from other cities that have excess allocation, kind of like was mentioned this morning, and looking at some type of reclamation and reuse. And also one of the technologies that we've considered is ice pigging. The amount of manganese and sand that we had in our system, some of that's still in the pipes. You still see iron and you still see manganese come through from the pipes. But the ice pigging is a technology where they introduce an ice slush through the municipal water supply, and that actually comes out on the ends. So that's a pretty quick run through on what we've done. But we've got some time for some questions. Nope. Down the sewer. Yeah, it's going down the sewer. We're trying to work with TCEQ. We'd like to do some ag application type of permits. Really look great on our park, if we could, and that may be an option for us in the future to treat the reject and then use that through an application permit.
While Wolfforth is a smaller community with fast growth, so you guys have a good base for funding, can you talk about some of the funding applications or things that maybe some towns or communities that might be interested in this could think of when it comes to implementing a project similar to this?
Yeah, it's a pretty expensive technology, as they all are. I think one of our issues we're a little bit too affluent to take any loan forgiveness or from the Water Development Board or anything like that. So in our situation, it's kind of been incumbent on us to just borrow the money and increase the debt load. But it's been a pretty tough in terms of funding, and these other additional situations that we talked about, like the pretreatment and those types of things, are going to be about the same way, because it's the affluence of the community that doesn't give you too many other options other than just debt.
Yeah, I wanted to know how much of the total cost of running everything is connected to the energy consumption. How big is this consumption?
Yeah, the energy consumption was not as bad as we thought. I was really expecting to see a major hit on our water or on our electrical bills. That wasn't as much of a problem as the pretreatment has come to be, and the labor that it takes to keep the stacks clean, to keep the filtration media cleaned all the time, and that type of thing. Our input costs have been not as bad on the energy, but much worse on the labor and the maintenance side of it and the materials. We spend on the pretreatment side of these, before the water goes into the stacks, there's 16 filters, 15 micron filters that they go through. It's $1,000 every time we change out one of those sets. There's 3 stacks, so that's been our high cost. And we really need to do a better job of protecting this system. It's an expensive system, but our next step after we get the pre-filtration done is to put in 3 more trains and just double the size of the plant. We're, like I say, at that 1.2 million gallon per day production capacity of it, and with the blending it's about 1.5 million, and we're already pretty much short of that, and we're really only about 4 years into production. Oh, it is. It's an actual desal. You could redesign it to be an actual desal plant. So these are used in other countries right now as desal. So that the technology is applicable. The size that we've got and the number of stages we've got has been scaled back to us because basically we're cleaning pretty clean water.
All right, thank you.
Thank you very much.